section 13.5. We're going to look at the effect of temperature on the rate of reaction. We've been looking at the effect of concentration. Most chemical reactions have rates that are very sensitive to temperature. If you think about a typical biochemical or biological reaction, a 10 degrees Celsius increase in temperature can double or triple the rate of the reaction. So that's a large dependence. The rate constant, K, is only a constant if the temperature remains constant. So if you change the temperature, the rate constant is going to change. If you keep the temperature constant, the rate constant is a constant regardless of the concentrations that you're dealing with. And usually rate constants increase with temperature, but not always. There are some reactions that go slower at higher temperatures, but those are not normal. They're not usual. So we have something called the Arrhenius Equation. And this shows the temperature dependence of that rate constant K. So we've been using this rate constant, and now we're going to be examining the rate constant. And the rate constant is equal to A times e raised to the power of negative EA over RT. So R is the gas constant, and we need to use 8.314 joules per mole Kelvin so that the units are going to work out. T is the temperature, and that must be measured in Kelvin. Remember, using the Kelvin scale gets rid of all the negative temperatures, and it gets rid of a zero temperature. If you threw 0 in here, what would happen? You'd have an undefined quantity because you can't divide by 0. So all temperatures have to be in Kelvin. So when we look at this equation, there are different parts. This A is called the frequency factor, and we're going to look at that. And the other part, e to the minus EA over RT, is called the exponential factor. In this exponential factor, the part that's not a constant, the part we haven't talked about yet, maybe I'll describe it that way. EA is the activation energy. We've got activation energy, and we've got the frequency factor. So let's look at what these things mean. So we've seen diagrams like this before. Here's energy increasing on the y-axis and reaction progress on the x-axis. Here we have some reactants, hydrogen and oxygen. They're going to react and form water. Overall, is this an exothermic or endothermic reaction? Exothermic. The reactants have higher energy than the products do. Where does the energy go? It goes out into the surroundings. A reaction in which the energy leaves and goes out into the surroundings is an exothermic reaction. But the energy of the reaction increases at this point. There's a hump that it has to get over, and that's called the activation energy, EA. It's the energy barrier that must be overcome in order for the reaction to occur. We're going to talk more about that. And then the frequency factor, A, has to do with the number of times that the reactants approach the barrier per unit time. So I think of this in terms of miniature golf. You know, at miniature golf course, they have all these humps, right, on the little putting greens. And you have to hit the ball hard enough to go over the hump, right? And so the frequency factor would be how many times you hit the ball towards the hump. The faster you hit the ball towards the hump, the more likely it is to go over, right? If you just hit it towards the hump once and you didn't give it enough energy, it's not going to get over. If you do it multiple times, the chances that you'll get it enough energy one time to get over is greater. So that's what the frequency factor means. The activation energy is how high the hump is. If you have questions, just interrupt me, please. So let's look at an example reaction. We're going to look at this reaction. This is methyl isonitrile, and that's an organic compound, and so there's no way that you should know that name, but we're just going to tell you about it. and this is acetonitrile. And there's one reactant and one product, and the only thing that's happening here is that the nitrogen and the carbon are switching places. In methyl isonitrile, the nitrogen is in the middle and the carbon is on the end. And in the acetonitrile, the carbon's in the middle and the nitrogen is on the end. Okay, so that's the reaction we're going to look at. What happens with this, as this molecule rearranges, is it goes through a high-energy intermediate state. So in order to rearrange this molecule, we have to weaken that carbon-nitrogen bond. There's a carbon-nitrogen, let's look at this guy. There's a carbon-nitrogen bond in here, this one right here. That needs to weaken because we're going to form a bond with this carbon. And so what happens is this carbon-nitrogen group is going to rotate. So here we see that the nitrogen is in the middle and the carbon's on the end. And here it's beginning to rotate. That requires some energy. This is called an activated complex or a transition state. And the energy of that is higher.
You have to put energy into that?
You have to put energy in order for that to happen. So the activation energy here is the energy needed to reach that activated complex. The higher this barrier, the slower the rate of the reaction, because you need more energy to get to that point. So there needs to be energy to twist this, to rotate it into this activated state. Once that occurs, it's downhill, literally, from there. It's all downhill, and it will go ahead and make this product. Okay, so that's the activation energy. The frequency factor, like I mentioned, is the number of times that the molecule approaches the activation barrier in a given amount of time. So we can think of it this way, that nitrogen-carbon group approaches the activation barrier each time it begins to rotate. So you could think of this a little bit like a tail on a dog, and it's going to move back and forth. Now, most of the time, it's not going to have enough energy to rotate completely to get to that activated state up here. But each time it wags, begins to rotate, is one approach. Some approaches are going to have enough energy to get over, and most of them are not. The frequency factor represents the rate at which that nitrogen-carbon group wags. So the faster this wags, the more likely it is that one of those is going to have enough energy to get over the hump. Yes?
Is activation barrier the same as activation energy?
The activation energy is the activation barrier. Yes. So that exponential factor, let's just go back here real quick to this guy. The exponential factor is E raised to the negative activation energy divided by RT. So that exponential factor is the fraction of molecules that have enough energy to make it over the activation barrier on a given approach. So it's going to end up being a number between 0 and 1. The fraction, it's the fraction of approaches that are successful. So the book gives an example. If the frequency factor is 10 to the 9th per second, that means that nitrogen-carbon thing is wagging back and forth. It's starting to rotate 10 to the 9th times in 1 second. That's really fast, right? It's like you wouldn't even be able to see that. It's just so fast. But not every one of those wags is going to have enough energy to actually complete the reaction. So the exponential factor, say, is 10 to the minus 7. What that means is 1 in 10 to the 7th wags has enough energy to get over the barrier. So the frequency factor would be like how fast you're hitting balls at the hump on the golf course. And the exponential factor is what fraction of those balls have enough energy. If the fraction is 0.5, then half of the balls you hit have enough energy to go over.
Can you just repeat that one more time?
About the golf balls?
The frequency and exponential is
So the frequency factor is how many times does the molecule approach that barrier in a given amount of time. We usually do it in seconds. So in this example, it's 10 to the 9th times per second. It approaches the barrier, tries to get over. The exponential factor gives us the fraction of approaches that have enough energy. So in this example, 10 to the minus 7th, that's a small fraction, right? 1 over 10 million. 1 in 10 million have enough energy to get over. So just looking at the exponential factor, you'd say, well, this isn't going to happen. But it does happen because of the frequency factor being so high. And so you've got these two factors that combine into the rate constant. So for this example, the rate constant would be the frequency factor times the exponential factor, and that would give you a rate of 100 per second, 10 to the 2 per second. Okay? So it's really helpful to understand what these pieces are and what they mean instead of just blindly doing algebra with the numbers. So the exponential factor is this guy right here, e raised to the power of the negative of the activation energy divided by R and T. So the exponential factor depends on the temperature and also on the activation energy. If the activation energy is low and the temperature is high, this factor is going to approach 1 because the numerator is small and the denominator is large. As this goes to 0, e to the 0 is 1. The smaller this gets, the closer this is to 1. At high activation energy and low temperature, this factor approaches 0. If the factor is 1, that means that every approach has enough energy. At higher temperatures, do molecules have more energy or less energy? They have more energy. So it makes sense that at higher temperatures, with the molecules having more energy, the fraction of them that can overcome that energy barrier would be greater. Here at low temperature, fewer of them will be successful. And if the activation energy is also high, then you've got two factors working against these molecules trying to get over this hump. Oops. So we learned in 1A that molecules in a sample have a range of energies, right? The temperature is a measure of the average kinetic energy of the molecules. And so we can look at an energy distribution, where here the fraction of molecules is on the y-axis and the energy is on the x-axis. And so at temperature 1, we see this nice curve, kind of a bell-shaped curve, that represents the energies of the different molecules. And so the average energy is going to be around it here, but some of them have low energy and some of them have high energy. The temperature measures the average energy. So at higher temperatures, the average moves up, but the other thing that happens that's important is the energy distribution is wider. The variation in energies becomes greater as the temperature goes up. So it's not just that we took this curve and we shifted it over, it actually spreads out and flattens. And so here we have the activation energy, and the area under this curve here is the amount of molecules that have enough energy to get over the barrier. When we increase the temperature, the fraction of molecules that can get over the barrier increases sharply. And this is why rates of reaction have a high dependence on temperature. They're very sensitive to temperature. Any questions? So this is a summary. The frequency factor is the number of times the reactants approach the barrier per unit time. The exponential factor is the fraction of approaches that are successful, that are energetically successful in getting over the barrier, and then the products will form. The exponential factor increases with increasing temperature, but decreases as the activation energy increases. Well, we did plotting of things, graphing of data and stuff last week, and so it's probably not a surprise that we're going to graph some data talking about this as well. So the Arrhenius factor can be graphed. So we can find the frequency factor A and the activation energy EA by measuring the rate constant at different temperatures. So let's see how that works. Let's see if I can remember how to do it. Okay, so here we have the Arrhenius equation. This has e to the mess in it. And so we want to get rid of that, and we're going to do that by taking the log of both sides. So I'm going to take the log of the left side, I'm going to get the natural log of k, and that is equal, here I've got a times this exponential factor. When I take the natural log of two things that are multiplied, it's the log of each of them added together. So that'll be the natural log of a plus the natural log of e to the minus ea over RT. So this guy right here, the natural log of e to the something is just that something, right? So you may think this is cheating, but it's not cheating. I can do it because I can do it. So that's going to be a minus EA over RT. Now, we want to be able to graph this. We can measure rate constants at different temperatures. And we want to find out what A is and what EA is. So I'm just going to rearrange this a little bit to make it look like the equation for a line. So the natural log of k, I'm going to reverse the order of these two things, minus EA over R, and I'm going to factor out the T. Everybody okay with that? Plus the natural log of A. And now we're getting something in the form of y equals mx plus b. So the slope of this graph will be minus EA over R. R is a constant. And the intercept will be the natural log of A. So there's the equation we come up with. We're going to graph the natural log of K versus 1 over T, making sure that we have our temperature in kelvins. The slope is going to be minus EA over R. The y-intercept is going to be the natural log of A. Well, what was A again? Remember? The frequency factor. How many times per second does this reaction approach the energy barrier? That actually does have some temperature dependence. But the temperature dependence of that is very small compared to the temperature dependence of the exponential factor. And so oftentimes we just ignore that temperature dependence. So A is going to change slightly with changes in temperature, but it's small enough that most of the time we can ignore it. So let's look at this example of how we can use an Arrhenius plot. So the decomposition of ozone here, O3 going to O2 plus oxygen atoms, is important in many atmospheric reactions. So Here's some data from a study of the reaction kinetics. We've got different temperatures and the rate constant at those different temperatures. And we are asked to determine the frequency factor and the activation energy for this reaction. So, hint here is that maybe we should make an Arrhenius plot, right? So practically speaking, how would we do this? Well, we would pull this data probably into Excel, would be the easiest way. And we would take these temperatures, and we're not going to graph versus temperature, we're going to graph versus 1 over the temperature, right? So we'd use an equation, and we'd find the inverse of all these temperatures. And the rate constant, we need the natural log of the rate constant, right? So let's just remind ourselves, we're graphing the natural log of k versus 1 over t. So we need to do some math on the data before we can graph it. When we do that and graph it, we get a plot that looks like this. We've got this nice straight line, and the program will give us the equation for that line. And now we need to find out what's the activation energy and what's the frequency factor. Well, what does the slope equal? Well, yeah, the value's there, but what is it in terms of the equation? Is it A or T or what is it? It's negative EA over R. And EA is something we're trying to solve for, right? So this one is pretty straightforward, so we could just rearrange that equation first and say that EA is going to be equal negative slope times R. Everybody okay with that? So the slope is minus 1.12 times 10 to the 4th. And we need a negative in front of that. What's the unit on that slope? Well, let's think about it. Slope is the rise over the run. What's the unit natural log of k? You take the natural log of something and units basically go away, right? So that doesn't really have any units. What are the units on x? 1 over kelvins, right? Oh, that's not what I'm going to do. So let's stick these units in here. So this would be 1 over rise over run. The units on the run are 1 over k, and if we're dividing by that, then we end up with k. Did I confuse you enough on that? No? I could try again. And what's R? 8.314.
Oh, the constant.
It's the constant. Joules per mole Kelvin. And the kelvins cancel out.
Putting this on YouTube later, right?
Oh, yes. This will be on YouTube later. And I encourage you to rewatch it and try to do it on your own without looking at the answers. Oh, that's a fabulous thing to do to an antique calculator. Oh my goodness. This calculator is older than most of you. Hopefully it's sturdy. It still works. Okay. Yeah, it lasted that long, right? Well, maybe it doesn't. Well, we'll deal with that later. We'll go with the new cheapy one. Well, I'm an equal opportunity calculator abuser, right? I dropped the first one on the floor, I got to drop the second one on the floor. This one still works. Okay. I promise, iPad, I won't drop you on the floor. 1.12 negative times 10 to the fourth times 8.314 equals. So, EA equals 93116.8 joules per mole. And then there's a negative in front here, so you got to change the sign again, and the negative goes away. Now, with things like this, sig figs become a little bit iffy, right? But we're going to give sig figs our best shot and try to be reasonable with them, right? So right here I've got, 6 significant figures. My graph had 3. If we go back and look at the data, these rate constants had 3, right? So it's probably best to round this off to 3 significant figures. And it's a big number, so let's put this into kilojoules. So this is going to be 93.1 kilojoules per mole. Everybody okay with that? Did I screw up? So that's one answer. And then they wanted the frequency factor. The frequency factor comes from the y-intercept, right?
Yes.
Y-intercept equals what? 26.8, but it equals the natural log of A. So then A must be e to the 26.8. There's somewhere, there you are. So this ends up being 4.36 times 10 to the 11th. What are the units on that? That's going to be hard to figure out just by looking at this, isn't it? Let's go back, not that far. Here's our rate constant. The rate constant is per mole per second, right? You know what? I'm blanking on this. It's per second, but I'm blanking on why. It's the frequency factor. It's the approaches per second. Okay, so that was wrong. We do need to look at the rate constant. We're doing this from the Arrhenius equation. The rate constant equals A e to the minus EA over RT. This is unitless, and so the frequency factor needs to have the same units as the rate constant. So we put units on this by going back and looking at the units on the rate constant, which were molarity to the -1, seconds to the -1. Okay? Any questions? So this is one answer, and this is the other answer. Sometimes you don't have the luxury of being able to measure the rate constant at so many different temperatures. And so you can use a two-point form of the Arrhenius equation. And your book goes through the derivation of this. And I made the executive decision that you probably weren't interested in watching me do that derivation. So I'm just showing you the two-point form of the equation. So the natural log of the rate constant at one temperature divided by the rate constant at the other temperature is equal to the activation energy divided by R times the quantity 1 over T1 minus 1 over T2. Now, where's the frequency factor in this? It's not there. In the Arrhenius plot, we assume that there's no temperature dependence of the frequency factor. And when we derive this equation, because the frequency factor doesn't change, it goes away, right? So with 2 points of data, rate constant at 2 different temperatures, we can find the activation energy. We can't determine the frequency factor just from that. And this is the equation we're going to use in lab tonight. So, yeah, that got some heads up. Okay, so real useful when data is limited. Tonight in lab, we're going to be determining a rate constant at just 2 different temperatures. But from that, we can use this equation and find the activation energy. So let's do an example of this. Reaction between nitrogen dioxide and carbon monoxide. And we're told that the rate constant at 701 Kelvin is 2.57, molarity to the minus 1, seconds to the minus 1, and at 895 Kelvin, it's 567. So, we've got a decent jump here in temperature, but the jump in the rate constant is huge. Find the activation energy for the reaction in kilojoules per mole. Well, the first thing we need to do is we need to identify which point is 1 and which is 2. It doesn't matter which you pick. I like to take the first one and make that 1. So T1 is going to be that first one, 701 Kelvin. And K1, rate constant at that temperature, is 2.57 m to the minus 1, s to the minus 1. T2 is equal to 895 Kelvin, and K2 is 567. When I ran through this at home, I wrote down the number wrong. I'm like, why don't I get quite the same number? Yeah, because I wrote down the rate constant wrong. So now we need the 2-point form of the Arrhenius equation. K2 over K1 is equal to EA over R times 1 over T1 minus 1 over T2, not 2. T and 2 both start with a T. Now, you could rearrange this equation and solve for EA and then plug the numbers in, but this is kind of a messy one, isn't it? So I'm going to say do whichever one you're better at. I'm just going to plug the numbers in and solve for EA. So we've got the natural log of K2, 567, divided by K1, 2.57. The units on those two are the same, and they're divided, and so those units cancel out. So I just canceled out the units. EA is what we're trying to find. R is 8.314. That'd be a real good number to memorize. Joules per mole Kelvin. And then we've got 1 over 701 Kelvin minus 1 over 895. Now, how you go about getting this into your calculator is between you and your calculator. If this guy will consent to work for me, I thought maybe he'd forgive me by now. So I'm going to take 567 and divide by 2.57. And then I'm going to take the natural log of that. And then I'm going to you may want to write that down over here, or you can just proceed without caution. I'm going to then multiply by 8.314, which is in the denominator over here. I'm multiplying to get it to the other side. And that gives me 44.866 and some change. And then I'm going to find out what this is and divide this into the other side. And I'm coming up with EA being equal to 145096.8. Anybody else get that number? Okay. Either we're both right or we're both wrong. Now, what are the units on that? Yeah, the Kelvin here cancels with this Kelvin. So those guys are gone. And so the unit we have on this side right now is 1 over joule per mole. When I multiply both sides by that over here, I get joules per mole. And so this is in units of joules per mole. But what does it ask me for? Kilojoules per mole. So that's going to be 145 kilojoules per mole. And we're just going to go for a reasonable number of significant figures. There's 3 in all of these guys, and so we'll just call it 3 and say that's good. Any questions? The important thing is understanding how to use the equation. If you're having issues with the algebra, we can talk about that during lab. You can refresh your memory on those things. I mentioned collision model last week. I'm going to look at it a little more here. This pertains to that frequency factor. So if we think about a gas phase reaction that has 2 reactants, in order for these reactants to react, they're going to collide with each other. And here we have a picture of these molecules colliding. Some of these collisions have enough energy to produce product, to get over that activation energy. Some of them do not, and they're just bumping into each other and going on their way and not actually reacting. We get the chemical reaction after we get a sufficiently energetic collision. So in terms of what we've been talking about, each approach to the activation energy is a collision between the reactant molecules. So each time the reactant molecules collide, that's one approach to the barrier. So if the frequency factor is 10 to the 7, or we'll just use 10 to the 7, that means that in 1 second there are 10 to the 7th collisions between reactants. Now this is between A and B. A and A colliding with each other, or B and B colliding with each other, they're not going to do anything, and so those don't count. Now, in practice, though, the frequency factor is usually less than the actual number of collisions per second. Any ideas why?
Because not every collision makes a reaction. So the frequency factor would be really less. Because some of the collisions per second get packed into the frequency factor.
Well, it turns out you can have a collision with the required amount of energy that still doesn't react.
Hit just right.
They have to hit just right. And so the thing that's missing there is this orientation factor. If they don't hit with the right orientation, it doesn't matter how much energy they have, they won't react. So in that frequency factor are two factors. There's this orientation factor P and the collision factor Z, and then here we have the exponential factor. So the orientation factor is the fraction of collisions with a favorable orientation. It's usually between 0 and 1. And the collision frequency is the number of collisions per unit time. This is usually on the order of 10 to the 9th per second for a gas phase reaction. So this collision frequency is the number of collisions per second, but it's modified by the orientation factor. Let's look at this example. Here we have NaCl reacting with NaCl to form NO and Cl2. In order for them to react, they have to collide in a way that allows the necessary bonds to break and the new ones to form. So if they run into each other with, let's see, the red in this one is oxygen, right? No, the red one's nitrogen. Usually red's oxygen on the model kits, and they're messing me up here. If it runs into each other with the nitrogen ends hitting, doesn't matter how energetically it happens, there's not going to be a reaction. If we've got a nitrogen running into the chlorine, we're not going to have an effective collision. We need to have the chlorine hitting with the chlorine because the chlorines are going to bond to each other. Okay? So the chlorine ends have to hit in order for there to be a reaction. For this particular reaction, that orientation factor is 0.16. That means 16 out of 100 collisions happen with the correct orientation. So that cuts the frequency factor down considerably from the number of collisions, doesn't it? Question?
Does that have to do with like their dipoles?
Does it have to do with their dipoles? I'm sure that plays a part, but it's not the biggest factor. I think here proximity is most important. Mm-hmm. That these two have to get close to each other in order for them to form the bond between the two chlorine atoms. So we've got lots of different factors going on. So if you have a very small orientation factor, that means that the reaction is very picky. Those molecules have to be aligned in a very particular way in order for them to react. If you have a reaction between atoms, that orientation factor is approximately 1. Are atoms symmetrical? Yeah, I think of them as marbles or styrofoam balls or something. They're spherical, basically, right? And so they don't really have one side that's different than the other. So if you have two atoms reacting and they're symmetrical, then no matter how they collide, their orientation is going to be okay. When you have a molecule, though, now it's going to, even if it's a nonpolar molecule, maybe two chlorine atoms, it still has some asymmetry to it. It's not symmetrical in 3 dimensions like an atom is. This one is really kind of mind-boggling. It's possible for the orientation factor to be greater than 1. And that indicates that an actual collision is not necessary. What? Right? That's like, what? So the book gives an example of this, and I just didn't feel like typing this whole thing into the PowerPoint because this is so tedious. It gives the example, I'll write it on here because that's faster. of potassium. This is in the gas phase. Potassium atom reacting with the bromine molecule to form potassium bromide and bromine atom. And it says the orientation factor for this is 4.8. So on the face of it, that really doesn't make sense at all. What they think happens is what they call a harpoon mechanism. And so the potassium here doesn't actually have to come in contact with the bromine atom molecule. It shoots or harpoons it with an electron, causing it to become charged, and then it reels it in by electrostatic attraction between the now positive and negative charged ions.
Take a lot of energy.
I don't remember ever hearing of anything like this, but it sounds kind of fun.
Is that only going to happen between large electronegativity differences?
Most likely, yeah. I can't imagine, bromine and something like nitrogen doing anything like that. and this is not something that, this isn't something that people would just think of and predict, right? They're studying these reactions and stuff comes up. They're using the Arrhenius equation and they're measuring these different factors and they're like, wait, this doesn't make any sense. And so then you have to get creative and think outside the box and figure out, well, this is what we're observing. How can we come up with an explanation for this? Now, is there proof for this harpoon mechanism? Can you prove a mechanism to be correct? We're going to find out that you can't. You actually can't prove anything to be correct. You can only prove things to be wrong. And so they'll stand as correct until someone can prove them wrong. But I just want to let you know that it is possible for that orientation factor to be greater than 1. It's not typical, though.